Alrighty, guys. So we have this reaction right here. So let's pretend you guys are doing this. So you got assigned the task of determining the enthalpy change. So enthalpy, you should automatically notice that it's about heat, right? Okay, so reaction between solid MgO and HCl. And this is the net ionic equation right here, okay? You do it in the styrofoam cup calorimeter. And basically you do it 4 times. You're good. Oh, Miles, there's a printout right here if you want to look that up. Okay, so you do it 4 times, and then this is the data that you get for all your trials, okay? All right, so what this question is asking us is which of these is the limiting reagent? Is it HCl or MgO? Okay, so super simple. This is just stoichiometry. So I'm going to cover that part up. So basically what we want to do is, since it's stoic, we want to get everything in terms of moles, right? So it's telling you that the HCl that you use, the molarity is 1 molarity. Okay, so you got 1 molarity HCl. So we got to turn this into moles, okay? All right, we know that 1 molarity is moles divided by liters. So what is the volume of our HCl? Yes, what?
What are you talking about? Oh, it's 100 milliliters?
Yeah, so it's 0.1 liters, yeah. My fault. I heard 0.1 milliliters, and so I was like, yeah, I was like, what? Hey, okay, I'm old, man. When you're old like this, you can't hear things either. All right, so we got this, and so we can calculate our moles. How many moles of HCl will we have? Yeah, 0.1. Okie dokie. All right, let's move on to MgO. So we got, let's just pick, I don't know. Which one should we do? Let's do number 2, because we always do 1. I want to make sure it's fair. We don't discriminate the number. So we'll do number 2, because it's the same one for HCl. Okay, so if we go to number 2, we can see the mass that we use is 0.5 grams of MgO. Okay, and then if we want to find the moles of MgO, what will we use for this fraction?
Molar mass.
Molar mass. Thank you. Thank you. All right, so the molar mass of MgO, I'll just give it to you guys. It's 40.3. 1 mole. So I'll give you guys a second to calculate that out. And if you have some time to think, or if you want to try figuring this out, just by looking at the ratios, try to just figure out which one is the limiting reagent. What is this? Do you want it? Do you want it, Claudia? Ian, can you give this to Claudia, please?
Okay, sure. I should have asked for it myself, but okay.
No, Claudia actually is very worthy of it.
What does that mean?
She wants the printer to pick up everyone's printouts.
Why doesn't that count this time?
Okay, so you guys should have gotten 0.0, excuse me, 124 moles of MgO. Okay. Something around there? Okay. Hello. All right, so based on that, we can take these values and we can analyze it using this equation. So basically we have 0.0, we'll do 12 moles of MgO, and we got 0.1 moles of HCl. Okay. Huh? Yeah, but then HCl is a strong acid that dissociates into H+. This is a net ionic equation. So the Cl stays aqueous.
Okay.
Good question, though. Okay, so based on these ratios, that means we need 2 moles of HCl in order to react with every 1 mole of that. But if you take a look at these values, which one is a lot smaller? Yeah, the MgO is significantly smaller than this one right here, right? It's 10 times smaller. Okay, so therefore, you can, just by looking at these numbers, you can already figure out MgO is going to be your limiting reagent. And then Robbie, I'll print it out for you right now.
Oh, okay.
Ian, can you go to the printer for me and then pull out the paper? Thank you. Okay, so there you go. That's going to be your limiting reagent. If you wanted to do all the calculations to figure out how much of a product you can make and compare, you can do it that way. But just by looking at these values, you can figure out that since you have far less MgO, that's going to be your limiting reagent. Okay. Yeah.
Can you simply say that for just one answer?
Yeah. Yeah. I would quantify it a little bit by saying like, oh, you have 10 times less, but the stoichiometric ratio is 1 to 2. And so that would be a good way to explain it. Yeah. Okay. Any questions on that? Not too bad, hopefully. Okay, let's go to part B. So part B, what we are looking at now is we're taking a look at this this table, and we're trying to figure out which one of these trials is inconsistent with the other ones. Okay, so this is it might be a little bit tricky, but I'll give you guys some time to look at it and think about it. I'll give you guys a hint though. Look at the temperature change. Okay, you're gonna need to look at the temperature change. So I'll give you guys about a minute or two. You can talk about it with the person next to you. See if you can justify your answer. Figure out which one of these 4 trials is inconsistent with the other ones. Okay, take about 2 minutes to do that. Okay. So the hint that I gave you for this one is we need to look at the temperatures. So let's look at the change. So here, what is the change in temperature? We don't need the approximate. What's the change in temperature here? 1. Okay, +1. Okay, we look right here. What is the change in temperature? About 4, right? 4.1. Okay, I'll write 4.1. Okay, what about this one right here?
2.1.
Okay, 2.1 or 2, something like that. And then what is the change in temperature here? 4. Okay. So just by looking at that, you can probably eliminate some of them, but let's go through all the data first. Now, the change in temperature is obviously going to be determined by how much energy is released in the reaction, right? And the amount of energy that's released in the reaction depends on how much of the reactants we use, right? So like if we had a bigger bomb, it would release more energy. If you had a smaller bomb, it would release less energy, right? So we got to take a look at the reactants and look at the difference between the trials. So here, we don't need to worry about the HCl because, first of all, it was excess and it's consistent throughout, okay? So we only really need to look at the mass of MgO per trial. So if we take a look right here, we got 0.25, 0.5, 0.25, and 0.5. So we got 2 of them that are 0.25 and 2 of them are 0.5. And so these are the ones that we're going to want to compare, okay? So let's start with the 0.5. So if you look right here at 2 and 4, when you have 0.5 grams of MgO, is there any difference in the change in temperature? No, not at all, right? So that means that these guys are probably consistent with one another, right? You have 0.5 and you're going to have about 4 degrees change in temperature. Okay, let's look at the 0.25s though. If you take a look at the 0.25s, there is a difference, right? And so the difference will be there's 1 versus 2.1. Okay, so it's going to be one of these because it's going to be inconsistent with the other ones, right? Okay, so now that we know that it's either 1 or 3, we're going to want to compare it with the ones that are consistent, right? So let's compare these, okay? So if we take a look right here, okay, what is the change in mass between the 2 trials? Yeah, times 2, right? So if you double the mass, this one is telling you that you quadruple the change in energy, right? Whereas here tells you double the mass, okay? You double the change in energy, right? Okay, yeah. Oh, thank you, my bad. Genius. Yeah, +4. Okay, but it's about the same, right? We can round that one down. Okay, so what we need to do now is we want to take a look at the stoichiometry because that is going to tell us how it's going to work. So let's take a look at the stoichiometry. Okay, if you have 1 mole of MgO, if you take a look at the products, what's the relationship between them? 1 mole of MgO produces how many moles of this product? 1. How many moles of this? Okay, so we can assume what kind of relationship will it have with the energy? Yeah, it's gonna have a ratio that's 1 to 1. So if we take a look at our data, we can probably tell that it's not going to have a exponential relationship if you double the mass. So the one that does not work is 1. 1 is the inconsistent one. Okay, make sense? Yes. Yeah, so let's go through the explanation. So first of all, you would want to be very clear about which one is inconsistent. So you say trial 1 is inconsistent. Okay, and so the way that we probably want to describe it is we want to refer back to the stoichiometry, okay? So you can talk about how the chemical equation shows us that MgO and the products have a, you can say, directly proportional relationship, okay? Okay, so you can say, and then you can say that, however, in trial 1, the change in mass has an exponential relationship with the change in temperature. Okay. Therefore, trial 1 is inconsistent. And if you want to add stuff about how the other ones do have a direct relationship, you guys can do that, right? Doubling the mass will double the temperature. You can also always add some more to that, but I'd say that's bare bones what you're going to want in there. Okay. Yeah.
I just like. I just put this 25 is before, and then 25 is after that, and then like the third file was 2, it's just like half before. 1.
Yeah, that works as well because you're still referring to the ratio between them, so that would be a perfectly good answer. Yeah, I'd say the biggest thing you want to just point out is the relationship between them and how it the mass and the temperature changes. Okay. You're staring at me so intently.
I zoned out. That's my bad.
Okay. Can you not zone out looking at me though? Oh. Sleepy guys. What's up?
Like, there's like it's
Uh-huh. Oh, is it the 2 confusing you? Yeah, so we can actually disregard the 2 because the 2 comes from the HCl, right? But here we can ignore the HCl because it's excess. So we're only looking at the MgO. So the ratio of the excess does not even matter. We don't care about this. Could be like 4, could be 1,000. It wouldn't make a difference because we're only looking at the relationship between MgO and how that changes the products. So basically we can ignore it because this is a constant. This is kept constant. We're just looking at how these are changing. Does that answer your question? Or
kind of, but like, how can you just like ignore it?
because it's held constant. We're not changing it between each of the trials, right? It's always going to have the same amount. So this is going to have, so it is going to affect the temperature change maybe a little bit, but the change is always going to be the same. Each trial, the HCl is only going to contribute the same amount. It's held constant. Yeah. Yeah, you would have to take the 2 into account if the HCl was changing, but luckily it's not changing here, so it's held constant, so we can ignore it in our okay, for sure. Cool. Yeah.
If it was inconsistent, I mean there was like an error during.
Yeah, most likely an error, contamination, human error, didn't wash it properly, something like that. Alrighty, you guys ready to move on? Okay. All right, so yeah, I just talk weird, guys. You guys just laugh at my English. All right, let's go to part C. Okay, so part C and D, we're gonna use data from one of the other three trials. So basically, we're gonna ignore the one that was inconsistent. So trial 1. So in this problem, it would it might screw you if you pick the wrong one. So just be careful. Okay, so we're gonna choose the ones that were not inconsistent. So 2, 3, and 4. And we are going to find the specific heat, or we have the specific heat of the calorimeter, 4.18. And then we have the density of HCl, and we're gonna calculate the magnitude Q, basically how much the change in thermal energy, change in heat. Okay, so you only need to do it for one of them. And so you can just pick one of them to find the magnitude of Q. So I'll let you guys try that out. This is calorimetry, so you're gonna want to use the equation for heat and specific heat. MCAT. Oh, you guys remember? Okay, so the heat formula, like Vivian said, is MCAT. Okay, it's a good way to remember it, actually. Okay, so what we want to determine here first is we want to figure out our variables, right? So we're looking for Q, so we want to figure out mass, specific heat, and the change in temperature. So basically, you just need to pick a trial to do. Did everyone do 2? Did anyone do 3? Okay, one person did 3. Oh, I gotta do both equations then. It's all good. I'm just kidding. I'm kidding. They're not. So it's okay. It's okay. But you only needed to do one of them, and I'll show you guys why in just a second. Okay, so we're gonna say trials 2 and 4 because they're gonna have the same mass. So we'll start with that, and then I'll show you trial 3 after as well. Okay. Okay, so let's start with our values. So we're gonna have to find Q. Now, before we start, we want to be a little bit specific about Q, right? We're looking for Q of the contents in the calorimeter, right? So when we're trying to find the mass, basically we're trying to find the mass of everything in the calorimeter. Okay, so if we take a look back at our values up here, since we picked 2, how many compounds do we have in the calorimeter? We got 2, so we need to actually add them up. Okay, and the reason why is because it tells you right here, the specific heat of the contents in the calorimeter, not water or one of the compounds, is 4.18. It's going to be for both. Okay, so that's actually half the credit for this problem. It's just recognizing that it's going to be the combined mass of everything in there. Okay, so let's start with the easy one. So the first one that's in there is going to be MgO, which is 0.5 grams. Okay, and we're going to add that to the mass of HCl. Now, this was actually another hint that you'll have to use both of them is because HCl, it gives you the density. Okay, so we have 100 milliliters of HCl, and it tells us that it's 1 gram per milliliter. Okay, so I mean, if we calculate that out, it should be pretty simple. It's 100 grams. Okay, so the difference would have been pretty negligible. But if you didn't have this in your answer, it tells you to take off a point. So that's about half the credit in the problem.
Wait, can you have that?
100.5 is fine as well, yeah. All right, so we got our mass. We're gonna plug in the specific heat, which is 4.18 joules gram Celsius. And then the delta T for trial 2 is 29.1 degrees Celsius minus 25. Okay, so those are going to be our values. Any questions about any of the stuff that we plugged in? You guys good? Okay. All right, so we calculate that out, and you should get about 1,700 joules. Okay, that's also equal to 1.7 kilojoules, something around there. Okay. All good? Yeah, so that was the big thing right here. Just be very careful when you're reading the problems. If it tells you the specific heat of the contents in the calorimeter, it's got to add up everything in the calorimeter. If it's just one of them, then you probably just need to use one of them.
So it's like explain which trial did or just like accept either.
I would recommend you to put down which trial you did, but if you have just if you just had that without writing trials 2 or 4, I'm pretty sure they'll be okay with that too. Yeah, there's no marking for that.
You have to write it.
No, one or the other. they really like it. So I recommend putting the units of measurement. Also, it'll help you check your answers, make sure everything's the same units. Yeah,
I got like 1,700 points.
that's close enough. Yeah. Specific heat, correct. Any other questions? Okay, I'll show you guys 3 and I'll show you guys why. It'll be different, but it won't matter too much, okay? And they'll accept both. You don't have to show both. Okay, so let's go back to our data. And so if we take a look at the mass, okay, this time for 3, it's gonna be 100 plus 0.25, right? Where am I? Right here, okay? So for trial 3, it will be 0.25 plus 100 grams, okay? And then if we take a look at it, specific heat is the same. Okay, and then the delta T here will be 28.1 minus 26, so it'll be 2.1. Okay, so I want you guys, even if you didn't do 3, just plug that into your calculator, see what you get, and I want you guys to see what the pattern was. I'm gonna round it up just so it's a little bit easier to look at. Okay, so you should have got around 880, about 0.88. So if you guys take a look at the relationship between these two, what do you notice? Yeah, it's about half, right? And if you guys take a look between 2 and 3, what's the difference in the mass? It's about half, yeah. So that's why that's the relationship between it. And so you could show it either way. Yeah, I know math is amazing. It's incredible. To see why my friends and I really like math. All right. Any questions on part C? You guys good? Okay. All right, let's go to part D now. I'm gonna give you guys about 3 minutes to try this one out too. I will give you a hint before you start just to save you a little time. Make sure that you guys are very attentive to the units of measurement that you're looking for, okay? Just be very attentive of the units of measurement. So I'll give you guys about 3 minutes to try that out, and then we'll go over it together. Also for this one, you could pick any of the trials, and I'll show you both of them if you guys want. Okay, so the hint that I gave you is to be very aware of the units of measurement. Now, while you guys are working, I underlined it. So the units of measurement you are looking for, so the delta H of the reaction is going to be equal to kilojoules divided by the moles of the reaction. Okay. Hopefully you guys noticed that. So how many moles of whatever compound you're looking for are in the reaction? Yeah, so we'll go over that in just a second, okay? Yeah, these moles. Okay, so if we take a look at kilojoules, since if we're looking for kilojoules, what do you guys think we should plug in? If you're looking for kilojoules, what value or what type of variable should we plug in? Yeah, heat, exactly. Yeah, kilojoules, same thing as heat. Thank you. Yeah, I'm not trying to trick you guys. Okay, so it's going to be the heat of the reaction, right? And then if you look at part C, that is where we calculated heat. So you should have noticed that our answer for C was joules, right? Or kilojoules. And so we can plug it in for kilojoules up here. All right, so if let's do this for trial 2 and 4. Okay, so for trials 2 and 4, the heat of the reaction was 7, or you got to do kilojoules, right? 1.7 kilojoules. Okay. All right, and then we're gonna divide it by the moles of the reaction. Okay. Okay, so for the moles of the reaction, you might be wondering, do we work in terms of the moles of MgO or HCl, right? Now, the reaction is dependent on which one of these reactants, MgO or HCl. MgO, why is it dependent on MgO? It is limiting, exactly. So here, when we are looking for the moles of the reaction, we only need to work with the limiting reagent, okay? So for trials 2 and 4, it was 0.5 grams of MgO. And then again, we're going to turn this into moles. Oh, did we write down the moles? What was the moles?
It was 0.01.
Thank you. 0.0124.
Yeah.
Thank you. Yeah, so if you have it from your previous data earlier, you can always bring that just straight down. Okay. Okay, so we're gonna punch that into our calculator. 1.7 divided by 0.124. Oh my goodness. Did I punch something in wrong? Yeah, something's off. 0.0124?
0.010.
Okay. Oh, messed me up. I was like, this one's the number's wrong. Okay. So yeah, you should get about 137, and then we'll go 0.1 kilojoules.
Like, how many points would they take off if we did that, like, screwed up a decimal?
Probably like half a point.
Mr. O, so I did like 1.7 because that's what I got when I did the option. If I got like 1.8.
That's close enough, yeah. As long as you're in the same ballpark. Mhm. Yeah, it's close enough. Yeah. All right. Now, one thing I do want to mention before we move on is if you take a look at the reaction, was it endo or exo? Was heat released or absorbed by the reaction? So if you look at the temperature, when you did the reaction, did the temperature go up or did it go down? It went up. So if the temperature went up, it is exo. Yes, so it's exo. So we got to put negative because it's releasing energy. Yeah, what's up, Mr. Rogers?
Oh, I was just gonna see, answer key for organic compounds.
If they don't need it, you can grab it from the binder. Okay. All right, so there you go. That is going to be your moles of reaction. Okay, so I want you guys to do the same thing, but I want you guys to do it for trial 3. Okay. So do it for trial 3, and I want you guys to compare the answers. Okay, so try it for trial 3, and then we'll go over together and talk about why you get the answer you get. Okay, 137 versus 140, 146. It's pretty much the same, especially considering the fact that we had double the amount of reactant in trials 2 and 4 compared to part 3. However, anyone want to take a shot at why? Why are they pretty much the same, even though you had double the reactant for 2 and 4? Yeah.
The bottom one is also like half of thing too.
Yeah, exactly. The heat is about half as well. And so this is, I wanted you guys to try this out because so you guys can take a look at this. This is the one that kind of standardizes the number. We're not looking at the energy per gram, how much of the chemical we use. We're talking about how much energy is released in the reaction per mole. Okay, so even though we're using a different mass, right? And we're using different heat that's released from different trials, because we're talking about the standardized reaction, we're looking at the moles of the reaction, you're going to have pretty much the same value. Okay, just keep that in mind. Yeah. All right, any questions on that? Okay, I think we're moving on to the last part of this FRQ. This is an example of a long FRQ, if you guys couldn't tell already. Yeah, it's pretty short, right? It's MCQ. Yes. 7 FRQs, 2 long, 5 short, 105 minutes.
No, but how much should we like take?
Depends. I don't know. I mean, if you want to calculate that out, the problem is like not all long FRQs are the same length as each other. not all short FRQs are the same length as each other, so
I know, but like you should take 1.5 minutes.
1 minute, 1 minute for each one. Yeah.
Are all of these this long effort, please?
I think, let me check, I'll pull it up. The one that we're doing right now, obviously long FRQ. The next one we're doing is a long, and then the last one is a short FRQ. Yeah, so 2 long, 1 short in the packet. Okay.
I know, is it 60 questions?
Yep, 60, 90 minutes. Yep. All right, let's do part E now. All right, this one I'm gonna do with you guys just for the sake of time. But if you guys want to ignore me and just try it out, please go ahead and do so. But yeah, just for the sake of time, let's go over it. Okay, so here we're looking at the enthalpy of formation in the reaction, and we have the table that tells us the enthalpy of formation for different compounds. Now, if you guys take a look back at the chemical equation, that's what we're going to refer back to here. So I'm going to write it down for me so I can refer back to it. H plus produces Mg2 plus H2O. Okay. Hopefully I copied that down correctly. Okay, so now we're going to take a look at the enthalpy of formation. Now, if you guys remember, this was a long time ago, back in unit 6. The enthalpy of formation is equal to the sum of the enthalpy of formation for the products, okay, minus the sum of the enthalpy of formation of the reactants. Hopefully this looks familiar. Okay, and if you guys notice, most of these delta things are products minus reactants because that tells us the change. Okay, so let's start with the products. Okay, so our first product in this reaction, I'll do this one in blue, is going to be MgO. Oh wait, sorry, not MgO, Mg2 plus, sorry, which is negative 467 kilojoules per mole. And since they're all kilojoules per mole, I won't write the units of measurement. Just make sure at the very end, your final answer has units of measurement, okay, since they're all the same here. Okay, now we're going to combine that. We're going to find the sum of that with the other product, which is H2O. And H2O is negative 286. So negative 286. Okay, and that's all of our products. Okay. And then we're going to subtract that by, and I'll do this one in black so that we can tell the difference between the reactants and the products. Okay, the first the first reactant is MgO, so negative 602. We're going to add that with H plus, okay, which is 0, but technically it's 2 times 0. Okay, yeah, but it doesn't really matter because it's still a 0. But I'll put that there. Just keep that in mind. Just be aware that, let's say if it was 2 MgO, you would have to double this. And so it would make a difference, okay?
Sorry, why was it 2?
Because the stoichiometry, there's a 2
Oh,
in the
yeah,
front. Yeah, no worries. Yeah. All right, so I will give you guys a minute to punch that into your calculator, see what you guys get. Make sure you have the correct units of measurement, and then we'll move on to the last part.
When we're adding up the products, we add with that. I guess since we're not subtracting, it doesn't matter if we do which like products we add to the other products.
Yeah, you can switch the products around. Like if you did,
You're always going to subtract or react to the products.
correct. Alrighty, guys. Final answer, negative 151 kilojoules per mole. Yes. Cool. Good job, guys. Alrighty, guys. So, before we move on to the last part, we're going to take a look at this value and we're going to compare it with our experimental value. So if we take a look at part E, our answer here, it tells us theoretically what the enthalpy of the reaction should be, right? So if everything went perfectly, it would be negative 151. But if you look up earlier, to part D, what was the experimentally determined delta H? Yeah, around 140, right? Roughly 140 kilojoules per mole. So if you guys take a look here, you're gonna notice that there's a difference between the theoretical and experimental. Okay, and so this is a thing that I want you guys to take a look at before we move on to the last part. Yeah.
No, it's something like sort of like.
Yeah, so in the range, yeah.
But like, it's always gonna be like relatively close.
It will be relatively close if the reaction's done well. Negative 151, yeah, they'll take that. No, that it wouldn't work that way. Yeah, if you do the numbers, no matter how you round it, you wouldn't get 151 for this one, for the experimental ones.
I know, but I'm saying like, could you shoot the scale for that?
Oh, for this one?
Yeah.
No, they're gonna want to see this work. Yeah. This, yeah, and this will be out.
Yeah.
The evil people that grade.
Society.
There's an American Chemical Society.
So can we
The
all
ACE.
still have Chem Society?
Yeah, you can.
Okay.
Them. All right. So just keep that in mind. This is the experimentally determined value. This is the theoretical value. Okay. So last part. Okay. So if the accepted value, so the theoretical value and the experimental value do not agree. Okay. Or they don't agree, right? Because we just established that with our numbers. If the calorimeter leaked energy into the environment, would it account for the discrepancy in the values? Would this be a legitimate reason why there's a difference between the theoretical and the experimental? Yeah. Yeah. Why?
Because,
Because the reaction didn't happen in a vacuum.
That's true, but why would energy leaving the system explain the numbers that we have here? Exactly, yeah. So if you guys notice, the experimental value is higher or lower? Lower. 140 versus 151.
No, it's 151.
151 was the theoretical, right? Oh,
Yeah.
I said it's higher. My bad. Experimental higher. Wait,
Wait, no, it's lower.
no, it's low. My goodness, now you guys are just messing with me. All right, it's lower. Yeah, okay. Around negative 140 kilojoules per mole. Oh my gosh, dude. I'm getting messed up. I'm trusting you guys too much. Yes, and if you did it right, the experimental will always be lower because it is physically impossible to do better than the theoretical. Okay. Repeated experiments throughout time have always shown we lose energy when we do
Is that what the
reaction.
Chem Society said?
That's what everybody says. Yeah. That predates the Chem Society. It's the second law of thermodynamics, entropy.
but what if I put in that I counted for the heat loss? So
Then you're still putting in more heat.
What is that?
Is lower than the theoretical value. Okay, which is 151 kilojoules per mole. Okay. Okay. Okay, if the calorimeter leaks heat energy to the environment, not all the energy is being used to heat or to raise the temperature in the calorimeter. Okay, and then you can finish it off by saying this would explain the discrepancy. You okay? You laughing at me making mistakes typing?
Well, he isn't-
It's okay.
well, I don't know, like, I mean, I have access. I threw up something.
He has access to my Patreon. He can go behind the paywall.
Oh, you should monetize the video.
Dude, I want to. YouTube puts ads on it. I've been told there's ads, but I'm not seeing a check.
What's the subscriber count you have now?
Yeah, I think it's like 1,000.
No, that's not true.
How many subscribers? Oh.
I used to edit for one of my friends, told me I have like 200 subscribers.
And he was monetized?
And he-
Bruh. Whack. All right.
You should make a website like Mr. Joe could make money for the website.
I should. And I should run a lot of ads on it. Sell your information.
Yeah.
Missed opportunity. Heimler's history. I don't know who that is.
Wow. Okay, no, no, you got.
No, I don't understand.
Yeah.
Okay, you got them.
Is he?
So he has this for.
He does.
Bunch of nerds.
Honest.
Can't stand nerds. Okay, I don't think we have time to do both of the other ones. Do you guys want to do the long FRQ or the short FRQ? Who wants to do the long one?
Are we gonna have time?
Yeah, we'll have time to finish the long one.
You learn more.
Okay, we'll do the long one. Alrighty, let us move on to this one right here. Okay, so this one right here. Okay, we are looking at intermolecular forces and molecular structure. So drawing. Alrighty, guys. So let's take a look at part A. Okay, so we are working with two different compounds, compound 1 and compound 2. If you guys look at the table, they have the same empirical formula, right? Okay, but they have different physical properties. What's the first different physical property you guys notice? Yeah, solubility. One of them is kind of soluble. The other one is soluble. Okay, what's the other one? Yeah, boiling point. One of them boils a lot lower. The other one boils higher. Okay, so we can actually draw some inferences about that. But we'll get to that later. Okay. So first thing we want to do for part A is we want to draw the structure. So what I want you guys to do is I'll give you guys about 4 minutes. I want you guys to finish by drawing the bonds for box X. And I want you guys to also figure out the other compound. Okay, I think that's part 2. Okay, so we're doing part 1 and part 2. So part 1, finish up this structure. Make sure you use all the electrons. And then valence electrons. And then for part 2, I want you guys to figure out the structure of the other one. Okay, the key to remember is one of them is slightly soluble. One of them is soluble. That'll kind of help you figure out or determine what these structures look like. So I'll give you guys about 4 minutes to do that, and then we'll go over it together. Okay, so you guys should hopefully remember how to do these. Now, you want to count up how many valence electrons you're working with. Now, since both of them have the same formula, you got 8, you got 6, you got another 6. Okay, so you add them up and you should get 20 valence electrons. Okay, each single bond is 2 electrons. So 2, 4, 6, 8, 10, 12, 14, 16. And then oxygen needs 8. So 18, 20. So that's X. Okay. All right. Part 2, you needed to create the other one. Now, if you guys notice, this one right here, is this a soluble one or slightly soluble one? No, this is very soluble. Yes, this is ethanol, actually. This is the chemical in alcohol that gets you intoxicated. And if you guys notice, it dissolves very well in water, right?
I knew you were.
We are not going to make ethanol, but we can. I have distilled it. So you can take out ethanol from the alcohol and get 100% pure alcohol. Yeah.
I'm sure it's like actually not that much.
It's actually very easy to make, but yes, it would be very damaging. All right. Box Y. So that means box Y has to be the one that is slightly soluble, right? Okay. So we need to create a structure where it's not completely soluble. Now, if you guys take a look at 1, what makes this very soluble? Hydrogen bonds. Yeah, wow. Okay, H bonds. Now, H bonds will form between the OH, right? Between me. Okay, I'm the reason this is very soluble. So basically, if you're going to make something that's slightly soluble, you cannot have me in that structure. Okay? Because I am the thing that makes it very soluble. Oh! All right, so you cannot have me in this structure. So this is already an inferior structure. Okay. Now, we still need to make hydrogens all around the outside. So anyone have any ideas? How can we make this slightly soluble? I can't see that far. Describe it to me, Vivian.
So on one side, we have C. C. C.
Yes, perfect. COC.
And C has 3 H's.
Perfect. Amazing. Woo-hoo! Yes, exactly like that. Perfect. There you go. Now, the key thing to remember here is the reason why there's no O's on, or hydrogen on O is because it is. Why does oxygen not have hydrogens?
It's electronegative.
It is more electronegative than carbon. So yeah, it doesn't want to share electrons with hydrogen. All right. So there you go. So it has some, it doesn't really, it's not very polar. There is a part of it, the middle, that is super polar, but it's surrounded by a pretty non-polar thing. So that's why it's only slightly soluble. Okay. Okay. All righty. Ready to move on, guys?
Mr. O, hydrogen bond O has N, O, and F, right?
Yes.
Okay.
All righty. Let's move on. Part B. Okay, so make sure you guys have the Lewis structures because we'll be actually I'm gonna just look at it. Okay, so I'm gonna read it and then we'll go back up. Okay, so based on the Lewis dot diagrams you drew, you need to identify which one of these is compound 1 and which one is compound 2. We already kind of did that. Which one is compound 1, X or Y? Y. This one is compound 1 because it is slightly soluble, and this one right here, compound 2. We kind of went through the reasoning why. But it's because of the hydrogen bonds that'll form here, okay? So you would just justify based on what we talked about. Compound 2 is soluble because it's going to produce hydrogen bonds. Compound 1 is only slightly because it doesn't have any hydrogen bonds, okay? All right, that is it for that one. All right, let's move on to the next part, part C. So here you have these structures, and now we're going to be taking a look at the structures and determining some stuff about the intermolecular forces at work. Okay, so dichloromethane has a greater solubility than water than carbon tetrachloride. Account for this observation in terms of IMF between solutes and water. So solutes just basically mean these compounds and water. So how do these compounds react with water, okay, which makes one of them more soluble than the other, okay? So dichloromethane, this one right here, is more soluble, and this one is less soluble. So I will give you guys a minute. So based on what you guys know about IMFs, I want you to explain why dichloromethane is more soluble than the other one. Okay, so take a minute to do that, and then we'll go over it. Okay, so let's take a look at this. So this guy is more soluble. Why is it more soluble? Yes, dipole. Another easy way of saying that is dichloromethane is polar. Yeah. Yeah, so you can say dipole, and so it it experiences dipole forces. Okay.
The same, like,
Oh no. You guys know it's dipole, right? Okay, I'm just saying my name because I'm pretty sure that's how you think of me. Dude, my name's on the door, bruh. No, my name's Paulo. Okay. All right, so that's why it is more soluble. Easy peasy, right? Dipole. Now you guys will never forget it. Okay, just think about killing me. Okay. I'm sure you do. I'm cool with that. Okay, in terms of IMF, explain why. Oh, actually, sorry. You should also mention here that carbon tetrachloride is non-polar. Yeah, so it is not soluble.
Wait, you have to write.
Whoa.
Dispersion for both.
You can mention dispersion, that they both have dispersion. But dipole is the one that really matters. Yeah.
I was gonna say, like, you don't know how to like directly extract the dye or could you like just do the roundabout way and say the other one is not, or you have to specifically like what else?
You would have to say that dichloromethane is polar. Even if you don't say dipole, you would have to recognize that it's polar, one or the other. You don't want to keep the great reader guessing. Yeah. Just pretend they're really stupid. Yeah, so you just tell them straight up what it is. You want to answer the question as direct as possible. Okay. Yeah, good question though. Okay, next one. Dichloromethane has a higher vapor pressure than carbon tetrachloride. Okay, so vapor pressure is when basically when it vaporizes above water, and then it creates that pressure. Okay, so I want you guys to try to write an explanation. I'll give you guys a minute to do that. We're almost out of time, and I think we might just be able to finish. Take a minute, try out writing your explanation, and then we'll go over it.